In this video, we will learn how to identify and illustrate the confounding patterns with the help of R. And for the sake of simplicity, we will limit ourselves confoundings between main factors and two factors interactions max. Also two factors with two factor interactions, but we will not consider confoundings with noisy effects such as 3 or 4 factor interactions. Okay. So let me start with, first of all, with loading the DOI tools again, the functions that we have written in DOI tools. And generating a simple design matrix with coded values. I will use the fractional factorial design for that, fract. And then I will use this as a pattern ABC and ABC. Okay. So remember, this is the design matrix. This is exactly the first design matrix we used in the lecture about the fractional factorial design, which is a half fraction design. Okay. Now, the first thing I want to do in this case, I would like to replace the column names of this matrix, because I know that every column represents main factor, and also it's very handy to know that this is just a combination of these three, so it's a confounded, right? For the confounding pattern, it's easy to work with the main factors names, and in this case I will just simply use capital Latin letters for the main factor name. So I say call names of DM, and then I say letters. Remember, I use letters, matrix letters or vector letters before, so I use it with the small letters like this, right? But R also has a similar vector for the capital letters. It's just you need to write letters with the capital letters. Okay. So we'll simply say, okay, from 1 to 4. Right? And now if you look at DM, now I have this A, B, C, and D. Now, how to find confounding pattern? Remember, we investigate confounding among the main effects, and also among the main effects and two-factor interactions, and also among the two-factor interactions, right? So it means that we need to have also matrix with interactions. And in this case, it's only two-factor interactions that we need. So we call it a contrast matrix, and then I will just simply get it using the function that we have already written, contrast matrix, and then DM, right? So you can see, let's check that it's correct. And then you can see it's correct, right? Now let's combine these two matrices together. I will call it AM, a matrix for analysis, so to speak. So I say combine DM and CMC, and then let me show you the whole. So here we have a full matrix with all main effects, and also all, not effects of course, but the levels of the factors for computing main effects, and also levels for computing the two-factor interactions. And you remember how we define the confounding. If two factors are confounded, in this case in two levels design, then they should have the same level. For every trial, they should have the same levels, right? So what it means? It means that if we multiply these two columns, we will get an identity column, right? So strictly speaking, if we want to identify all confounding patterns, we need to multiply every column of this matrix to every other column. That sounds like a tricky task. However, for this case, it's not that tricky, because what we can do, we can take a cross product. We already did that, right? Let me show you what it gives you. Cross product AM. I'll remind you that when we do the cross product, first of all, we transpose AM, so rows becomes columns and columns becomes rows, and then we multiply it to AM itself. So it means that this will be a row, and then we multiply to this one as a column. So it means that we will have all pairwise multiplications, and it's not just a multiplication, it's a dot product. It means that we multiply elements of these rows and columns element-wise, and then we take a sum. And you remember, if we take a sum of identity column, we will get 8, because we have 8 trials in total. But if we have a sum of any other columns which are not confounded, we will have 0. So strictly speaking, cross product will be a matrix of zeros and 8s. And let me show you that, right? So I think I need to make it a matrix, because by default it's a data frame, I believe. So let me just say S matrix. So this is it. Look, what we have is a matrix 10 by 10, because we have 4 main factors and 6 interactions. And then you can see that all diagonal elements of this matrix are 8s, because apparently A is confounded with A, B is confounded with B, or CD is confounded with CD, right? But look, if you take the row which corresponds to main factor A, you don't see all other multiplications, all other dot products are zeros, because you remember, in this design we don't have any confoundings between main factors, and also between main factors and two-factor interactions, and that's what we see here, right? But let's look at the AB. You can see in this case we have two 8s. First of all, AB is confounded with AB, it's itself, but it also is confounded with CD. That's why we have these two 8s here, right? And then the same here, you can see that AC is confounded with AC, but it's also is confounded with BD and so on. So this matrix actually provides us all information that we need. We just need to extract this information correctly. Let me keep it, let me call it CP, means confounding patterns, okay? Now, how we can do that? Of course, we need to treat it row-wise. For example, let's take row number 5, which is AB. CB 5. Okay, so this is row number 5. I need to run it again. This is row number 5. Now, the idea is following. Let's take the names of the columns where this row number 5 is equal to 8 or just above 0. That's enough, right? So if I do it like this, you can see that I will get like false, 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 and then true where we have AB, and then true where we have CD, right? So what I can do, I can say, show me call names of CP where this row is larger than 0, right? And this will be all the effects our row number 5, which is also AB, is confounded with, right? And then look what I can do. I can combine this together using function paste 0, which we used already many times. But instead of separator, I say collapse equal to plus. You will see an effect in a minute, right? So you can see that it merges all the elements of this, and then it adds plus in between, only in between, right? So now I can combine it with another thing. I can combine it with the call names CP number 5, which is my original factor, and then equal, and then this one. It looks a bit tricky, but you will see in the result in a minute. You can see effect from AB is equal to effect from AB plus effect from CD. This is exactly the notation that I use in my lectures, right? So now what we need to do it for every row of the matrix CP. And also you can see that I extract call names several times. Maybe it's a good idea to do it one time only and save it somewhere. For example, I can save, for example, effect names equal effect names equal to, for example, call names of matrix AM, because matrix CP and matrix AM will have the same call names. So that's one thing. And then I can say for row goes from 1 to number of rows in CP. That will be the loop. And then I will just change this. Instead of call names, I use effect names. Instead of 5, I will use this row. And then here I will do the same. So in this case, I say effect names. Instead of 5, I will use row. Let's check if it works, right? So let's see. And then the only thing we need to do, that's the reason why we don't see anything here, is inside the for, if we use paste, it returns some value, but it doesn't show any value. So I need to say show or print. Okay. I think now it should work. And it does indeed. The problem is that it shows you this extra information and it shows you these quotes and so on and so forth. You can make this output a bit nicer if you use a function cat instead of show. But in the end, before we end this paste, we need also to add a new, this /n, it means make a new line. So now look how different how clear the output is. So A is confounded with A, B is confounded with B, or in other way, effect from A is effect from A, effect from B is effect from B, effect from C is effect from C, but effect from AB, it's a sum of two effects from AB and CD. And then you can see it's exactly what we have also seen in the lecture, right, in the video. What we can do now? Now we can make it more versatile. Let's make it a function. Function, for example, print confounding patterns. So for any design matrix, that will be our main argument. It will show these values, confounding patterns. And then look, you can see that here I define the column names, redefine the column names. First of all, instead of 4, I need to say and call of DM, because it can be different number of columns. And then maybe it's not always necessary. Maybe if you provide dm with real names like temperature and concentration, you would like to see the real name. So let me add a new argument. For example, call name or names as letters. And it will be logical. If it's true, then I will replace names of the factors with letters. If it's false, then I will don't do it. Okay. So then I will just check it. If this is true, names as letters. If this is true, then I do this replacement. Otherwise, I keep the original names. Okay. I think that's about it. Let me just cut and paste it to the DOI tools somewhere at the end. Like this. Save it. Go back. And then let's check. So say, first of all, we need to reload it, of course. Make a DM matrix and then print confounding patterns. And then DM, like this. And then, for example, if I say names as letters equal to false, it should give me the original names, and you can see it does, right? It does. Now I switch back to true, like this, and then let me use a design. Let me use a design, for example, from the bicycle example, right? AB, AC, BC, and ABC. And then again, if you open my lecture and look at the confounding pattern for the bicycle examples, you can see this is exactly what I actually had, right? Moreover, we can do the following. We can say this is, let me just keep it, and then let's say dm1 equal to dm, dm2 equal to dm, and then let me change the AB to minus AB, right? So it means that dm2 AB equal to minus dm2 AB. Remember, I just introduce a fold over. And then I will combine these two matrices together. R-bind, dm1, dm2. You will check that this is indeed a fold over now. You can see that everything, this one starts with 1 and then follows -1, but from 9 you can see it's -1 and then 1, 1. So we have a matrix with fold over now. And then if you look at this design pattern here, confounding pattern, not design pattern, of course, you can see that indeed everywhere you have D, now it's resolved. So D is not confounded with anything, AD is not confounded with anything, BD is not confounded with anything, and so on and so forth. It's exactly what I also showed you in one of the last videos. Okay, so now we are fully equipped for the full and fractional factorial design. And then in the next learning sequence, as I said, it will be a very short one. We will first of all consider several extra designs, and also we'll do some cleaning. So in the next learning sequence, we will clean this code that we have written so far, maybe do a couple of small improvements, but also add some like comments and help information. Okay.